All right, let's dive into something pretty cool today. We're going to trace the incredible, super high-speed journey of a single network packet as it makes its way through the Linux kernel.
I mean, have you ever really stopped to think about what's going on when a packet hits your server? We see network traffic all day, every day, right? It's so easy to just take for granted this unbelievably complex dance that's happening inside our machines millions of times a second. So what is that dance? How does a bunch of data from a cable actually get to the application you're running?
The best way to think about it is like a relay race. Seriously, our little packet is the baton, and it gets passed from one super specialized runner to the next. What you're looking at here is basically our race map. It shows the 5 key stages we're going to break down, from the moment it hits the network card all the way to your program.
Okay, so our race starts right at the physical layer. The packet has just come in off the wire and landed at the network interface card. You know, the NIC. Its very first challenge? It's got to get from that piece of hardware into the computer's main memory.
So how does it do this so fast? Well, there's this key piece of tech called Direct Memory Access, or DMA. Just think of it like an exclusive, high-speed shuttle bus. The NIC uses DMA to just place the packet data directly into RAM, completely sidestepping the main CPU. And this is absolutely crucial for efficiency, right? You don't want your powerful CPU getting bogged down with the boring job of just moving data from one place to another.
So, okay, where exactly in memory does this packet land? It gets put into a special, pre-reserved waiting area called a ring buffer. I like to picture it as a circular conveyor belt, kind of like at the airport baggage claim. The NIC is the one putting the bags, our packets, onto the belt, and the kernel comes along and picks them up for processing. It's a beautifully simple and super fast way to handle that data flow.
Okay, so the packet is safely in memory. Great, but now we've got a bit of a problem. How does the CPU even know the packet is there waiting for it? And this right here is where we get to the core conflict of our whole story.
See, the old school way of doing this was for the NIC to basically ring a doorbell for every single packet. This doorbell is a hardware interrupt, an IRQ. And here's the kicker. When that bell rings, the CPU has to drop everything it's doing, I don't care how important it is, and go answer the door. I'm sure you can see where this is going, right? With thousands or even millions of packets flying in every second, the CPU ends up spending all its time just answering the doorbell over and over again. It has no time left to do any real work. This is what we call an interrupt storm, and it is a huge performance killer. So the big question is, how on earth did Linux solve this mess?
Well, the solution is a really clever mechanism, and it's pretty much the hero of our networking story. It's called NAPI.
And this really gets to the heart of what NAPI did. It was a fundamental shift. We go from that totally chaotic interrupt for every single packet model to a much saner and more efficient system of processing things in batches.
You can think of NAPI as a really efficient manager. Instead of letting the NIC just interrupt it constantly, the kernel, through NAPI, basically tells the NIC, hey, look, don't call me for every single thing. I'll come and check the ring buffer for new packets myself when I get a chance. This switch from being bossed around by hardware interrupts to doing its own software polling was a game changer. It's the kernel taking back control, saying, I'll decide when to process packets. Thank you very much. And that is the key to handling today's high-speed networks.
So here's how it actually works. The very first packet that comes in triggers one single normal interrupt. That's the signal for the driver to go, okay, we've got work to do. It immediately tells the NIC stop sending me interrupts for a bit, and then it kicks off a software polling loop. This loop just chugs through the ring buffer, scooping up all the waiting packets in one big, efficient batch. And only when the queue is totally empty does it turn interrupts back on, ready for the next wave of data.
All right, so now our packets are being pulled from that ring buffer super efficiently. The next stage of our relay race can begin, and that is the climb up through the software layers of the network stack. This part of the journey is really like climbing a ladder. Each rung is a different protocol layer doing a specific job. You've got the network layer, which is like the map. It uses the IP address to figure out where the packet needs to go. Then there's the transport layer with TCP or UDP. That's kind of like the delivery service, making sure the data gets to the right application port. And finally, you hit the socket layer, which is basically the doorway that hands the data off to your actual program. But wait a second, what happens if a single CPU gets totally overwhelmed trying to do all this ladder climbing work? Well, that's where another cool feature comes in, Receive Packet Steering, or RPS. It's a powerful, software-only feature that acts like a traffic cop. It starts distributing the incoming packets across multiple CPU cores so they can share the load. This ability to parallelize the work is a total game changer. It stops one core from becoming a bottleneck and lets you really maximize your server's processing power, even if your network card only has a single queue.
So, there you have it. We followed the packet all the way from the wire to the application. But why does any of this actually matter? Why should you care? Well, because understanding this journey is what gives you the power to find and fix real-world performance problems.
And the key to that power is a fantastic command line tool called ethtool. You should think of it as the main control panel, the diagnostic dashboard for your network interface. And specifically, the S flag shows you all these incredible statistics for every single step of the journey we just talked about.
And you can see just how powerful it is. When you run the command, you get this big list of counters. Let's say you see the RX dropped counter going up. That's a huge red flag. It's telling you, clear as day, that packets are making it to the ring buffer, but the kernel just can't process them fast enough, and the buffer is overflowing. Or, hey, maybe you see RX missed errors climbing. That tells you the problem is even earlier. The NIC itself is getting overwhelmed. With this one command, you can pinpoint exactly where things are going wrong. So now you've got the map and you've got the tools. You understand this incredible relay race that a packet runs through your system, from that first DMA transfer to the smart batch processing with NAPI and then the parallel workload with RPS. The only question left is, where's the bottleneck in your system? Where are you going to look first?